So we can see the figure. Although the voltage has a huge precision, but the output current is very good, right? Very close to sinusoidal. So this is the wonderful of the matrix converter. So we do not need any DC link capacitor. So we have output current based commutation. We also have input voltage based commutation. Because we know the voltage should be VAB, and it could be next one VAC, and then VBC. So we have to determine the input voltage. When should we switch? So we use input voltage sensor to detect the input voltage, and then we can determine the switching pattern. So this is input voltage based commutation, and we also have 4 steps. So like this. So here we want to change from A phase to B phase. So we can detect A phase and B phase. When they are equal, then we switch from A to B. However, because the circuit has, we call noise. So sometimes it is not so good, not so pure. So in general, if you can switch in this area, then we say it is okay. Not at this point. Because sometimes the sensor has noise. And then from here we should change from B phase to C phase, and then C phase to A phase. So this is 4-step voltage commutation technique. Okay. So we still have some problem. What kind of problem? Sometimes if your matrix converter has short circuit, then what happens? Damage. Do you like to damage? No. Then everything just gone. So your advisor gave you one topic. How can you protect the short circuit? If there's short circuit, but the hardware is still okay, right? How can you protect? So this is short circuit protection. If your gating power supply fail, then you could short circuit. Then what happened? So how can you prevent you lose the power supply voltage? And how can you protect if output is too huge? So overload. But you cannot use freewheeling die, right? Because you use AC switch. For DC switch, you can say I can use freewheeling die. So if this turn off, but I have some current, then the current can go this way or can go this way, right? We call this is freewheeling diode. They provide the path when these two switches turn off. But you are AC switch, do you have freewheeling diode? no, then what can you do? So you have no natural prevailing path. So when you have that time, then all switch turn off. If all switch turn off, then you create LDITT. Then you have spike here. Then the spike will damage every device. So how can you solve this problem? So sometimes our energy is not balanced. Sometimes input is larger than output. Sometimes output is larger than input. If input is larger than output, so input is larger than output, then what happens? So your input here, your output here. So input is larger than output, so you have more current to charge capacitor, right? Then the capacitor voltage increase. So this is input larger than output. If your output larger than input, you need more power, but your power is not enough. Then what happens? Your voltage drop. Then you have huge capacitor. Huge capacitor is like a leg. A leg. If you have a huge leg, then you have a huge leg. Then the leg say, okay, I will absorb every water, no problem. Then you have 5 time interval. Then the leg say, it's okay, I will supply water for everybody. So huge leg can regulate water, right? So your huge capacitor can regulate power. If you have input power, then the capacitor say, it's okay, I will increase a little voltage because I'm huge. If your input is smaller than output, then the capacitor say, I can supply power to the output. So the huge capacitor has its function, its ability. But now you remove the leg. So huge city, no leg. Then what happens? If the raining come in, then everywhere flooded. If it is dry period, then we do not have water. So it becomes very complicated. So you can see we have no capacitor, then we have no storage energy. So input should be equal to output. If input is larger than output, then the voltage increase. If input is smaller than output, then the voltage drop quickly. And then we create a lot of spike. Where can the spike go? Everywhere. Then they will damage your device. So your main circuit becomes very weak. So this is the real problem. So how can you solve this kind of problem? If you cannot solve this problem, then your matrix converter becomes useless. So how can we solve the problem? So anybody has any idea? Because you have no capacitor, so you cannot store energy. If you cannot store energy, then you have spike. The spike will go everywhere. So what can you do? So anybody has any idea? So you say your circuit is perfect. So you have 9 switch. So you have 9 switch. And you have output current, but you have that time. So the output current can be changed immediately. In this case, you create a lot of spike. So the problem is, how can you reduce the spike? So you have 9 switch. But you say, if you need to turn off the switch, then it takes a little time to turn on this switch. And at the same time, this off, this not on. This off, this not on. Then what? Spike, right? If you have spike, then it could damage your device. So you still need a snapper, right? So how can you design the snapper circuit for a matrix converter? We can easily design snapper circuit for inverter. So how can we design snapper circuit? We have phase diode, we have capacitor, then we have resistance for each device, right? We discussed this before. So we call this is what? Snapper. How can you design snapper for AC switch? How can you design snapper for AC switch? You say, I have no idea because it is so hard. AC switch, what is AC switch? AC switch include this one and this one, and the AC switch include this one. So it is so complicated. So how can I design the snapper? It is impossible. So what can I do? So one student, he go back to his home and propose idea. So he said, if we have energy, we can put the energy into capacitor. So we just put the energy into capacitor. So we put energy to small capacitor. So I have to draw again and to draw more clearly. So we have this one, this one, this one, and we have capacitor. And we have this one, we have this one, we have this one. So we have one bridge for input. So this is for input. So we can use this one to connect to this one connect to this one connect to this one. So this is for input, and this is for output. So we have A phase connect to here, B phase connect to here, C phase connect to here. So if you create any spike, then the spike will charge the capacitor, right? Because the spike can go here or a loop. So if you have any spike, the spike will automatically create a loop to charge the capacitor, either input side or output side. So this is for input, this is for output. So if you have current, the current will go this way, will go here, and then maybe go here, and then they automatically charge the capacitor. But the capacitor voltage become higher and higher. Then finally become infinity. So what happens? So you have to detect the voltage. If the voltage is too high, then you have to turn on the switch to use the resistor to absorb the power. Then the voltage will drop. So you can use a resistor to release the power. So we call this is clamp circuit. The clamp circuit is equal to snapper circuit, but it is for matrix converter. So people design clamp circuit. And how about the capacitor? Only need 2 microfarad, very small. If you use DC link, what is your capacitor? 1000. But here only 2 micro. very small. So it is okay. So we can use very small capacitor to design the clamp circuit. Then everything will be fine. So this is clamp circuit. So now everything is ready. How about the layout? So we have a lot of switch. If you have switch, then you use a line. So you have AC switch. You have a line to connect the switch. Then the line becomes what? Inductance. Inductance. Straight inductance. If you have two lines, then the two lines become what? Straight capacitor. So you can see you have straight inductance, straight capacitor, then it creates ringing. So you can see the waveform. Originally you want to create this waveform, but finally the waveform becomes this way because ringing, because of straight inductance and the straight capacitor. So you cannot use line. If you cannot use line, what can you use? You have to use, we call small resistor, but not inductance. So you have to use bus bar. And we will see what is bus bar. Bus bar can remove straight inductance. Bus bar can remove straight capacitor. We will discuss this later. So if you design matrix converter, what is important? Layout is important. You cannot use traditional method to do it. You have to use bus bar. Bus bar. So we will check. This is the real photo of the matrix converter. So you can see every device use copper. So this is copper. Copper very thick, so it is a copper. If a copper you put a device here, then between the copper, no inductance. Only small resistor. And the resistance is almost zero. And then no capacitor. So you can see this one is bus bar. So we use very thick copper bar to become bus bar. So you have to be very careful about your layout. So you can see if you turn on, then no overshoot, no reading. You can see from 0 to 6 and so forth. Then no reading. If you do not use bus bar, you use a line and reading. So you have to care about your straight inductance and the straight capacitance. Okay? Then we will discuss about modulation. So how can we determine the switching pattern, the PWM for the matrix converter? So before we discuss about inverter, inverter has many different methods, right? We have sinusoidal modulation, we have space-based, right? We have band control. How about matrix converter? So we will discuss about the modulation method. So a lot of researchers propose different method. So can you propose a new method for matrix converter? If you can, then you can graduate tomorrow. Do you like to do this? Yes, it is very interesting. Okay. So what is ideal matrix converter? The switch could be 1, the switch could be 0. Output is current sink. Input is voltage source. So we assume the voltage is voltage source. The output is current sink. Okay. So then we can obtain the main circuit. So it is very simple. We use AC switch. So how can you use mathematical to describe it? you can say the output of VA is SAA multiplied by VA plus SPA multiplied by VB plus SCA multiplied by VC. The B phase is SAB multiplied by VA plus SPB multiplied by VB plus SCP multiplied by VC. How about VC? The output of VC is SAC multiplied by VA plus SPC multiplied by VB plus SCC multiplied by VC. We discussed this before. How about current? So the same way, right? Input current is SAA multiplied by IA plus SAB multiplied by IB plus AC multiplied by IC. So the S switch, when they turn on, it is 1. When they turn off, it is 0. So we can say SAA plus SPA plus SCA equal to 1, right? SAB plus SPB plus SCB equal to 1. SAC plus SPC plus SCC equal to 1. So we have general rule. So we have learned it. So no problem. So how can you determine the switching pattern? Then we can say we can put AA, BA, CA. So AA plus BA plus CA equal to 1. AB plus BB plus CB equal to 1. AC plus BC plus CC equal to 1. Then how many unknown parameters? 9, right? But you only have 3 equations. You have 9 unknown. How many solutions? No solution. So what can you do? Then we can copy. We say this one, we move to this one, right? We discussed before. This one copy to this one, and this one copy to this one, and then this one copy to this one, this one copy to this one, this one copy to this one. Then how many unknown? 3. So we only have 3 unknown. Then have unique solution. So this is the general rule. Otherwise, it is too challenge. How about the period? This one plus this one plus this one. How much time? In general, if it is 2 milliseconds, so 2 milliseconds, okay, is 500 hertz. So if it is 2 milliseconds, it is 500 volts. If we need 2 kilohertz, what is 1 period? 0.5 millisecond. What is 0.5 millisecond? It means 500 microsecond. So TAA plus TPA plus TCA is 5 microsecond. So this is regular rule. This one plus this one plus this one is 500 microsecond. This one plus this one plus this one is 5 microsecond. We call it is equal to T sequence. So T sequence equal to 5 microsecond equal to 2 kilohertz. So when we design, we choose this kind of rule. Why you choose 500 microsecond? Why? Because you need a lot of computation, right? When you compute duty, do you remember what is related to duty? Output voltage, input voltage, output frequency, input frequency, and the time, right? You need to do cosine, you need to do a lot of math, then you need 500 microsecond. Because your DSP cannot execute the computation too quick. So then we have the relationship. We can compute output voltage. We can compute input current. We have some rule. SAA plus SPA plus SCA equal to 1. So we have learned this kind of basic idea. Okay, so now we have some question. What is output voltage? say it is equal to input voltage multiplied by Q. Q is voltage ratio, right? Do you think Q is larger than 1 or smaller than 1? Output voltage is larger than input voltage or smaller than input voltage? Do you think output voltage could be larger than input voltage? Impossible. So Q is how much? 0.5. Because your worst case is 0.5. So this is 0.5. And then you can change output frequency, any frequency. So this is your output voltage. How about your input current here? Input current is related to output current, right? If output current is larger, how about input current become larger? And also related to the power factor. This is input power factor, output power factor. And this is input frequency, 60 Hertz. And this is input phase angle, right? So you can see this is input current and this is output voltage. So we can calculate the output voltage and the input current. So what is the problem? The problem is Q only 0.5, right? Why Q only 0.5? Because your waveform is like this. If this is 1, how about this? 0.5. The minimum point is 0.5. So do you feel happy about your half cut to 50%? You say no, I don't feel happy. So I need more voltage. How can you get more voltage? You can put harmonics. So we will discuss this later. And another issue is, how can I control the power factor? If I use the regular method, then input phase is equal to output phase. So if I drive a motor, the motor output voltage and the output current, it is 30 degrees there. Then what is the power factor? The power factor is cosine 30 degrees, 0.888. Then how about the input? Then input voltage has the same pattern. We have input voltage, then we have input current. This is also 30 degrees. Then what is your power factor? Your power factor is cosine 30 degrees. So how much? 0.866. Then you say I don't need 0.866. I need 1. I need unity power factor, right? So how can you get unity power factor? So anybody has any idea? Then you can control the switch, right? Original we say 1, 2, 3. Then you have 1, 2, 3. Then you have 1, 2, 3. But at the next step, you have to change 1, 2, 3. Then you have to move. This become 2, 3, 1. This become 3, 1, 2. Right? We mentioned about this one. So you have two patterns. And you have to put this 0.5, this 0.5, half. And then you can get unity power factor. So this is the fundamental method. And one student proposed this idea. Then he can get a PhD. So now we have some issue. So if we have unity power factor, then what happens? Then it is very good because we do not have any reactive power. If we have their power factor, then which means the load is inductive, right? So we have P and then we also have Q. If we have leading power factor, then which means the load is capacitive. we have P and we have Q. And this is positive Q, this is negative Q. So I need unity power factor, so I have to switch. So this is the fundamental idea. So we can obtain unity power factor. And another issue is here. We have minimum point here, right? Minimum point here. So in this case, the peak amplitude cannot over this one. If the peak amplitude over this one, we call it is overmodulation, right? So we have limit here. Then the peak value become how many? 0.5. Which means you remove half voltage. If your input is 220 volt, how about your output? The maximum is 100K. So do you like this? No, it is too small. Then what can you do? You have to propose some method. And I tell you, maybe you can put some third harmonics here. If you put third harmonics here, then you can increase this point, decrease this point. So you can see if you put third harmonics, then what happens? You have a waveform like this, but you put some third harmonics like this. Then your waveform could be changed like this. Then it becomes higher, right? Then you can get higher voltage. So how can you inject the harmonics? So it becomes a new research. So what is the optimum value? So one student, he picked up this problem and become his PhD dissertation, and he proposed. So the solution is here. How can you inject the harmonics? You have to inject output frequency. How many times? 30 times, right? 30 harmonics. And what is the amplitude? 1/6. 1/6. And then how about the next one? Input frequency. The 30 times. And this is the amplitude. And then he used the math to prove this is the optimal one. If you do this, then you can get the maximum DC value. So he used the math to prove this. If you do this, what is the peak value? 0.866. Original is 0.5, right? So you can see original is 0.5. After I injected this, become 688. So what is the ratio? 1.73. I increase 1.73. Is it good? Good. So this is the solution. So the maximum value become 87%. 87%. So this is one student. He focused on this issue. He used the mathematical analysis to solve the feature, and he showed this is the optimal voltage. Okay, so this is the idea. So we have to add triple harmonics, third harmonics, and the third harmonics is injected in phase. But for the line to line, they will cancel each other. So in line to line, you cannot see any third harmonics, only phase voltage. You can see the third harmonic. So this is very good idea. So what is the method? You have inject this one related to output. This is the amplitude. This one related to the input. This is the amplitude. And put together. Then you can reach the 0.866 of the input voltage. So this inventor, his name is Bertrand. I think he comes from Italy. So this is his name. So So people use his name to say this method. Venturi Ultima Amplitude method. So he proposed this method. So we can increase the DC voltage. How can you increase the DC voltage? You have to inject third harmonics. So third harmonics. Then you can calculate the amplitude and find the ultima of the DC bus. So this is the general idea. So he is the first person who proposed this idea. So finally, he changed the switching pattern. S11, S12, S13, S21, S22, S23, S31, S32, S33. So he changed the switching pattern. And then what is the result? Okay, so this is the result. This method has some disadvantage. This method is not symmetrical. If the switching pattern is not symmetrical, what happens? It creates odd harmonics and even harmonics. So in general, we hope the switching pattern should be what? Symmetrical. Then we can remove even harmonics. So what is symmetrical? Symmetrical means every waveform should be balanced, right? So another people, they propose a revised method. We call this is Shinnick Bernoulli method. He modified his method. You can see this becomes symmetrical. So then he can remove the even harmonics. So this is the modified method. And this is another way to make sure they are balanced. So this is double side Shinnick Bernoulli method. So this is another way. So what is the time domain? After you do the Shinnick, what happens? This is negative, right? This is positive, this is negative. Very clear. Before you use this is negative, but how about this one? Positive. So you create a negative and a positive, they will cancel each other. Then it becomes a waste, right? You can see here. This is positive, but how about this one? Negative. So if this is positive, should be every pulse go positive, right? And here, this is negative, but this is positive. But after modify, it is very clear. So you can see the difference. So if you use symmetrical, then it is better. So this is, we call modified method. And another way, we watch the video, they call space vector. So what is space vector? You think A, B, C become one vector, right? And the vector can rotate. So they use space vector. So we call this space vector. So what is a space vector? We have voltage and the current. The current has a vector. It comes from ABC. The voltage has another vector, come from ABC. So both of them are rotated. Then we can determine, we have 27 possible vectors. And it can be separated into 3 groups. The first group, each output line is connected to a different input line. So if A phase, then it could be to A, and then to B, and then to C. So they have different input. So this is group 1. And group 2, 2 output lines are connected to the common input. So A connect to A, right? And B connect to A. So two, you can see group 2 is two output lines are connected to a common input line. Okay? And the group 3 is all output lines are connected together. So A, B, C connected together, then it becomes zero vector. Zero vector. So we have three groups. The first group is each output line is connected to a different input line. The second group is two output lines are connected to a common input line. The third group is all output lines are connected to a common input line. So total is how many? 27, right? So then we can use the space vector. What is space vector? So you see very hard. So you have 27. So they can list here. Total is 27. And then you have to decide how to do modulation. So you have to calculate. So this is the general idea. So you use math to calculate. And then you have vector. So this is output voltage. This is input current. So each one has 6 regions, right? And we watch the video. The video say in this vector, a lot of opportunity to obtain the same vector, right? So you can see this one. Then how can you determine how to switch? So it becomes this one. So if you use space vector, it is symmetrical here. And this one and this one met. So it is symmetric, right? This one equal to this one. You can see all three, V4, V4, V3, V3, O2, O2, V2, V2, V1, V1, O1, O1, the same name. So they are but symmetric. So you have to use math to determine the switching pattern. So this one we call double side 3-0. This is double side 2-0. So they have different ways to synthesize the same space vector. So now we have a comment for space vector. So do you think a space vector is easy to implement? It is not easy because the vector, the switching is not unique. So you have your own, I have my own, but we have the same result. So the solution is not only one. Different implementation are possible. And the different implementation give different high frequency or distortion. And a common mode addition to output target is inherent with space vector method. So if you use space vector, then it is good because your DC value becomes 87%. The same as the harmonics. So this is very good. And freedom to control input current vector relation can be beneficial and distort unbalanced input voltage. So some students study if input voltage is not balanced, then we can change the switching pattern to improve the unbalanced problem. So there are some research in this area. So this is a space vector. And then your advisor asks you, can you propose one? You say, I'm empty. Then you cannot graduate, right? So what should you do? Go back to sleep and then think again. So one student, he go back and sleep to think again. Finally, he proposed one method. He said, for the switching, I have one switch always turn on. I only change the other two switch. Then what is the advantage? If the switch, this switch do not turn on or turn off, the switching loss is what? 0. Then they can reduce the switching loss. So this is ideal, right? We have 3 persons, but 1 person also take a break. Then it is good. So you can see this switch always turn on. How about another 2? They will share the responsibility. Then it is symmetrical, but the loss is minimum. So we can see this is minimum, middle, maximum method. So he is the author, Oyama. Oyama could be a Japanese, right? He is a student, but he proposed this idea. So he attempts to minimize switching loss. So he minimized communication by having only 2 output phase switch. The third phase is always on or always off. So he minimized the voltage change and minimized the switching loss. So this is one way he proposed to reduce the switching loss. And another method is frictional method. What is frictional? Frictional method is if you have a matrix converter, then I think it is too complicated. So I can image the matrix converter equal to rectifier, and the inverter. So here we have the voltage like this, right? Then I know how to switch this. I know how to switch this rectifier. Then I use this multiple by this become matrix converter. So AC to AC it is too hard, but I can think AC to DC and DC to AC. Then we can use these 2 stages to synthesize the switching pattern. But this is only in your brain. In the physical, we only have this. But in switching, we can consider this one. So this is the idea. So we call fractional DC link modulation. So we have A matrix and a B matrix. B matrix change DC to output. A matrix change AC to DC. So then we use combination to determine the switching. So A multiplied by B. And then we create the DC link fraction method. So if we use this method, then we can get the DC link is almost 0.7, because then this way we can increase the DC link. And we can obtain Q could be 1.05 input current. And then we call this is fractional DC link modulation. Okay, so this is another way. Do you have another way? No. So this is the most important. Then we have to compare which one is the best. How can you compare? We can compare output voltage harmonics, right? Do you need high or low output harmonics? Low, right? So you can compare this one. You can know which one is better. If you use Vertanium, you inject the harmonics, but your output harmonics is very huge. If you use space vector, then it is good, right? So space vector is better than Vertanium. And how about minima maxima? Minima maxima is here. It is huge. So if you care about output voltage harmonics, which one should you use? Space vector, right? So you can see the comparison. So sometimes we compare with another issue. We compare about input current harmonics. If you care about input current harmonics, then which one is better? This one. So what is this one? Space vector. Which one is worse? Quaternary. So you can see, how about MMM? Middle. So you can compare. If you care about input current, then which one is the best? So then we can watch another one, and we will stop here. So this is what? Loss. So device loss. If you have a lot of switching, then your loss become higher. If you have low frequency switching, then your loss become lower. So which one is better for loss? So you can check this one. The best one is which one? Minima, maxima. So the switching loss is minima. Which one is higher loss? Space vector modulation, and consider about balance, cynic, quaternary. So this one is too complicated. It needs a lot of switching. Then the switching loss is higher. MMM, the switching loss is lower. So if you consider different issue, you should use different method, right? So you can see the comparison. So I think we can stop here. I will see you next week.